Just recording. All right. Okay. All right. So yeah. So this is kind of like set of slides number 2, cryptographic tools and ideas. All right. So remember that we're thinking about cryptography in terms of the principles of information assurance. So those are the things that we're trying to achieve or protect or defend. So cryptography provides the building blocks to achieve security, network security, etc. We've looked at privacy and confidentiality with symmetric encryption. We haven't looked at authentication, but that's coming up. We haven't looked at non-repudiation, but that's coming up. And then we've looked at integrity. That's basically the idea of hashing, okay? So, yeah. So to summarize, symmetric encryption, okay, the universal technique for providing confidentiality for transmitted or stored data, right? So that should be clear to you guys. Also referred to as conventional encryption or single key encryption. So far you've seen in the algorithms, or in OpenSSL, we only had one key. 2 requirements for secure use. We need a strong encryption algorithm, okay? And the sender and receiver must have obtained copies of the secret key in a secure fashion and must keep the key secure, right? So usually the algorithm is well known, but the key needs to be kept secret. So this was the framework that we looked at before. So if it's a simplified model of symmetric encryption. So we've got plain text input goes into an encryption algorithm such as DES, right? You need to have a secret key shared by sender and recipient. Notice it's K, it's the same from both sides. Then we transmit the ciphertext, which is basically the result of encrypting the plain text and with the key. And that is received on the other end, and it's going to have to be decrypted. So it's a reverse. So we need an algorithm to reverse the process and obtain the plain text, right? So we that summarizes symmetric encryption. Now, attacking symmetric encryption. So how can you do that? Basically, you can cryptanalytic attacks. So we kind of gave you an insight into that, right? Looking for patterns in the data. There should be no patterns, right? If there are patterns, it's not a secure cipher. So exploits the characteristics of the algorithm to attempt to deduce a specific plain text or the key being used, okay? If successful, all future and past messages encrypted with that key are compromised. So that's cryptanalytics, searching for patterns. Another approach is just brute force, right? So try all possible keys on some ciphertext until an intelligible translation into plain text is obtained, right? So that's like you somehow guess the key out of all the possible keys, right? So eventually, maybe this would be possible if we had quantum computers, for instance. I mean, in fact, the government has passed like a policy or a law maybe that all encryption algorithms need to be ready for quantum in about 15 years, I think. So that's kind of like saying they're afraid that in 15 years, quantum computers will be available and they'll break all of cryptography. So this may change, right? If that happens, but it hasn't happened yet. All right, so anyway, so these algorithms are essentially, this is what we use today, but if they're broken either through brute force or cryptanalytics, there's trouble. All right, so here's some statistics. Average time required for exhaustive key search. Obviously, this changes with more computing power, right? But this is just in general, it gives you an idea. So obviously, the thing to look at here is the key size versus the amount of time it takes to decrypt it. So the idea being that the bigger the key size, the harder it is. Okay, so you can see from 32 bits to 168 bits, it tells you the number of alternative keys that you have. So notice those are very big numbers. And then you have the time required, so you can see it goes from milliseconds to years, basically. Okay, so it becomes a thing of computing power. Okay, or very smart algorithms. Because all of cryptography is algorithms, basically. I mean, there's one topic that is basically just the algorithm software that's available. All right, two of the most important techniques in symmetric encryption. Basically DES, the data encryption standard, and AES, the advanced encryption standard. They're both block encryption algorithms. Okay, there may be other variations of these, but in general, they both have the same idea. Okay, that you break the message into blocks, you perform XOR. We will look at DES. Okay, and you will see it's a very highly elaborate algorithm. We will not look at AES because AES does a lot of matrix multiplication. So like the math becomes pretty advanced. Okay. And implementing it in code, like in Python, would be stressful. But just like we did the hash integrity XOR Python script, we will do some parts of DES later in the semester. Okay. Just to kind of understand how it works. Yeah. So AES is DES is no longer used, okay, because it was broken some time ago, and so but they're both very highly studied approaches. Okay. So this is a comparison of three popular symmetric encryption algorithms. Remember, all of these are symmetric. That means they're block ciphers. That means they use one key that must be on both sides. All right. SSL uses symmetric key encryption as part of the overall framework, right? It's just that SSL also has to have a component for authentication and has to have a component for sharing the secret key securely. And that's something we haven't learned about just yet, but we will when we study RSA. So as you can see, really what changes with these, I mean, the algorithms change a little, but important things are the plain text block size, the ciphertext block size, and the key size. And notice they don't have to be the same size. I mean, they can be modified in the algorithm, okay? But in general, they do get bigger, right? So, DES was a certain size, and that was a reflection of the technology of the times, the 80s, 90s. And then triple DES was just doing DES 3 times. And then with the idea being that they break one, but then they have to break another. And by the time they get to the third one, you've already created a new key, right? So just delaying things. And then AES, the advanced encryption standards, it's like, as I said, a different algorithm, but still using XOR and block ciphers, just a little bit more. Okay. So the data encryption standards, so historically, we can talk about this one a little bit. The most widely used encryption scheme, I mean, it's still available in some hardware, right? So it can be still available in some places. Referred to as the data encryption algorithm, uses 64-bit plain text blocks, 56-bit keys to produce a 64-bit ciphertext block. Strengths, concerns about the algorithm. DES is the most studied encryption algorithm in existence. And what that means is, remember I said this, right? That in cryptography, you don't obscure the algorithms. It's actually not a thing you want. A good analogy of this is like Windows to Linux, right? So I don't know if you guys know, Linux is open source, right? And then Windows the code is protected because it's Microsoft. So it used to be back in the day that Windows had a lot of bugs, and that's because fewer people were able to look at it. Whereas Linux it's open source, a lot of people looked at it and fixed the bugs, right? So it's kind of like that. So an encryption algorithm should be studied quite a bit, right? So that people can find that weakness or vulnerability. You don't want that to be there, okay? So really, these algorithms, like DES was broken and then it was replaced, and AES was proposed, and it's harder to break, right? And so really, an RSA, for instance, as far as we know, it hasn't been broken, right? And so could be that some governments have broken it and they just don't tell you. So that's a possibility, but as far as people know, it hasn't been broken, even though they do try to break it. And it is encouraged that, you know, they do competitions. At some point for RSA, we'll even look at how it can be broken, like some of the theory of it, the practicality of it. Actually, you will do that in the scavenger hunt. You will break RSA because I'll give you a very simple breakable key. All right, so the size is important even there as well. All right, yeah, so basically in 1998 that it was broken. DES was broken around 1998. All right, and so then they did AES. So here's another just a figure of the relationship between the key length in bits and the number of years to break. So the idea being that the bigger the key, the harder it is to break, right? So that's really something. So that's why the keys keep getting bigger and bigger. But performance is an issue as well. So you have to kind of watch out for it. And Claude Shannon said with the one-time pad that if you have a key as long as the message, then that is almost like perfect secrecy, but it's just not practical. So there is that element. Okay, triple DES, as the name implies, is just a DES algorithm 3 times. They change the key and so on. So repeats basic DES algorithm 3 times using either 2 or 3 unique keys. Okay, and the idea is it just takes longer. This was kind of like in the early 2000s, like a quick solution until they had a AES, you know, a new symmetric encryption. Okay, and then it's obviously drawback. The algorithm is sluggish in software, you know, because it's slow, you know, it's taking 3 times as long. And when you're encrypting a whole bunch of data in a network, that can have an impact. Remember that, right? So if you're encrypting stuff, it'll slow down things. All right, then comes the advanced encryption standard. This algorithm is more advanced. So basically what they did is they created a set of ideas of what they wanted, and then people submit a solution, right? That's how it works. So people say like, this is the ideal things that we want, and people start producing results. For instance, RSA. RSA actually is the names of the people that created the algorithm. And they just proposed that, and that was the best. So basically, they said that they needed a replacement for triple DES. Triple DES was not reasonable for long-term use. It was just kind of a quick fix when they broke DES. So that NIST, the Institute of Standards, right, they kind of govern such things. So they created called for proposals for an advanced encryption standard. What they wanted was symmetric block cipher. So this tells you a lot, right? Already you know the type of algorithm they're looking for. Significantly improved efficient, should have a security strength equal to or better than triple DES. And they wanted keys that were, you know, bigger, basically. Okay. And as you have more computing power, that becomes possible. In the end, they selected Rinsdale in around November 2001 and so on. Okay, so this is how this works, basically. And then today you see a lot of, there's newer algorithms, but they're all kind of built on, they're all symmetric block ciphers, for instance, right? So if it's a 1 key, it'll be like that. That has been shown to be the fastest encryption available. So and it's secure, or as long as you can securely exchange the keys. That's the key. So encryption happens, even though we're going to look at other algorithms. Encryption happens, confidentiality, I should say, happens through symmetric block ciphers. Okay, this is still used for encryption. There's nothing different. All right, so this is, I always like to throw in this cartoon. So Bob and Alice are basically like how you talk about cryptography. Everybody likes to say Bob and Alice this. So yeah, so the idea is you have Bob and Alice, they want to talk to each other, and then you have Zelda, and she's trying to intercept the message, right? So a lot of our problems will revolve around this idea. right? So you can take a look at the cartoon if you'd like. All right, so now let's take a look. We're gonna go back, kind of summarize symmetric key encryption, summarize integrity and hash functions, and then lead in to our new problem, which we will begin next week, right? Which is how to exchange the keys. So you guys now know everything about symmetric encryption. You're experts in that, right? We've done a few algorithms, and but you need to now exchange the keys securely as well with your friends. And this is another partner type of a lab, right? So we're going to move in that direction. So the properties of symmetric encryption. So we've established the pros of symmetric encryption, which is confidentiality, pretty good at that. Zelda can, and I'm going to speak in terms of Bob and Alice and Zelda. So Zelda, remember, tries to steal the data. So Zelda cannot access the message without knowing the key. So that is the pro. Authentication, only whoever knows the key can participate in the communication, right? So that's kind of a type of authentication. All right. Integrity, if the message C is modified, it will decrypt to gibberish. Okay. We still need to do this problem. But you can see in our algorithm today, right? Like if I was to modify something, we're XORing with all the blocks, right? So we're going to affect the final result. We will do this problem on Thursday, or maybe start it today, I'm not sure, where we take, just like we did before, we're going to take something, hash it, then we're going to corrupt one bit of it, hash it again, and see what happens. All right, so we're going to go back to that same exercise. The cons of symmetric encryption, or secret key encryption, or block encryption, kind of similar name. The con number one, key distribution is critical and requires out-of-band communication. So what that means is like almost Bob and Alice have to like meet beforehand at a coffee shop and exchange the key. There's no other way to securely do it, right? So, and even then somebody could be eavesdropping. So that's the challenge. So this is the problem that symmetric encryption does not solve for you. And so we've got to find a better solution. If key is compromised, then Zelda can impersonate Alice or Bob. That makes sense. You're sending a message across the world. They intercept it. They have the key. They can change it, which basically means they're impersonating either one. And it cannot be used to prove that the message was sent by specifically one of the involved parties, right? So the non-repudiation issue. So that also is not addressed by symmetric encryption. So we need better tools for that. Any questions, guys? All right. So practical security issues. So we've already talked about this. So I'm just kind of summarizing. Remember, there's modes of operation in symmetric encryption, right? Typically, symmetric encryption is applied to a unit of data larger than a single 64-bit or 128-bit block. Obviously, for our examples, we've used like 8 blocks, just 8-bit blocks, or blocks of 8, just because it's easier, but you usually want something a little bit bigger. We know that there's 4 modes of operation, ECB, CBC, right? We've kind of looked at those. The ECB, which is the electronic codebook mode, is the simplest approach to multi-block encryption. So we still need to do that encryption scheme, kind of by hand. So we'll go over that at some point. Don't need to do that. Each block of plaintext is encrypted using the same key. Okay, and cryptanalysts may be able to exploit regularities in the plaintext, right? So that's something that we already saw when we were able to see the triangle and the circle still in the encrypted image. Okay. Modes. So we've looked at 4 modes of operation, and they're basically alternative techniques developed to increase the security of symmetric block encryptions for large sequences. We know that ECB is insecure, that this is basically an image and then done AES, but with ECB, you can see that there's a pattern there, right? So what can you see? You can see like the outline of the hair. Again, this does not meet Claude Shannon's definition of a secure cipher, because you can infer something about the original plain text from the cipher, and that should not be the case. All right, so we're going to look at a few other concepts. So this is a new concept. So we've got block ciphers and we've got stream ciphers. And stream ciphers are another type of encryption that can happen. So the difference here is with block ciphers at the top, block cipher encryption, what do you have? You have the encryption and decryption part. So you have the encryption up here. Can you guys see my mouse? No? I guess not. All right. So you got the encryption at the top, and you can see basically you take the message, you break it into blocks, and you're XORing each block with the key and getting a cipher. Do you see that? But there's no relationship. Like you're not using C1 for the next step. Do you see that? Like P2 just takes the key, encrypts it, and produces C2. PN just takes the key, encrypts it, and obtains CN. They're independent in parallel. So what's the problem with that? The problem with that is, think about it. The key is the same, right? You guys see that the key is the same? The encryption algorithm is the same. So what if, for instance, P1 and P2 are both the letter, or they're the word hello. They're both hello. And you're XORing hello with the same key. What would you say about C1 and C2 in that scenario? Think about it. If the key is, so look at these two, right? The first two, P1 and P2. So the key is the same for both. The encryption algorithm is AES or DES, the same. And if P1 is the word hello and P2 is the word hello, then what would you say about C1 and C2? What are they going to be? Are they going to be the same or different? Same. That's where we get this problem with ECB, that we can see a pattern. Like if the original message is the same, the cipher will be the same. So that's the problem with ECB. Other modes of operation, what they do is, here for the P2, we'll use P2 and the key, but it can also XOR with the previous C1. You see that? And that can then, get rid of the patterns. Even if it's the same plane, it's not going to be the same cipher. But for the very first iteration, we need a block, and that's going to be the initialization vector. Okay? So it's similar to what we did in the hashing algorithm. So we'll come back to this idea, but hopefully that makes sense. Okay? And then for the decryption, notice we have the C1, C2 to CN. We have the key. It's the same. We decrypt, and now we obtain our P1, P2. So that's symmetric block cipher encryption. Then we have the stream encryption, and that's a different approach. Basically, the definition of it is that we do a per byte encryption. So basically, we take our text 1 byte at a time, and we take our key 1 byte at a time, and we XOR them. Do you guys see that? That's the idea. However, we can't have a key that is the same length as the message, right? So for this to work, because we may have a message that's really long, what we are going to do is we do have a fixed size key, but then we have an algorithm called the pseudo-random byte generator. And what that algorithm does is that it starts with a key, but it just produces a byte. It's the same, it's a deterministic algorithm in a sense, right? That given a key, it'll just start generating bytes as a function, basically. Think of it as a function, and it just generates a byte and 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 a byte. So the way that this works is you can look at plain text here, which is plain text M, and that's the message. Could be a movie, could be a book, could be 3 pages, whatever it is. And you can think of that as bytes. So you just take the first byte of that sequence, and that first byte of the sequence goes into here, right? The XOR operation. you have a key of, say, size 128, whatever it is, but then you have this algorithm called the pseudo random byte generator. And all that algorithm does is, given the key, it produces a byte every time. Like, it's going to start with this byte, then another byte, then another byte, and so on. And so you're encrypting that byte with the byte of the message, and that produces a byte. That's why it's called a stream. And then that byte gets sent to the other end, and then on the other end, you're going to take what? The byte, right? And the same algorithm for pseudo-random generator, same key, should give you the byte, right, that you got over here. So you XOR them now, and you decrypt the message. Does that make sense, guys? So the definition, so if I ask you on the exam, what is the stream cipher, you can just say something like, it's an algorithm that encrypts on a per byte basis, right? And it uses a pseudo-random function to create, basically it's creating, if you notice, a key as long as the message itself, except that that key is generated through a function, right? You don't have an actual key, you have a function that generates bytes. Any questions on this one? No questions? All right, so that's one important definition. That's one of the 4 modes of operation, right? So if you look at some of the modes of operation, they said something like stream in there, and that's because they were based on this. Okay. Do you need padding on a stream cipher algorithm? Probably not, right? Because, you know, if you think of a byte as a letter, then why would you pad? That's one of the advantages of it. And that might be why some of the modes of operation just didn't pad, if you remember, okay? Because they're doing it on a per byte basis instead of a block basis, if you will. Okay, but the very important is the pseudo-random generator is the function that does this for us. Okay, block and stream cipher, so just a few little like contrast. Block cipher processes the input 1 block of elements at a time, size 8, 16, we've done this before. Produces an output block for each input block, can reuse keys, it's more common. Stream cipher processes the input elements continuously, right? Produces output 1 element at a time, okay? A primary advantage is that they are almost always faster and use far less code, and basically encrypts plain text 1 byte at a time, as I kind of indicated. Okay. Yeah, so that's kind of the 4 modes of operation that you had. They're still considered symmetric. Okay, both of these. All right, so that's kind of symmetric encryption. It was just a review, kind of to and now we're going to look at message authentication, also a review. This is the integrity part. So basically hashing, if you will, protects against active attacks. Verifies received message is authentic. For instance, key aspect is that the contents have not been altered, right? That's key. It's from authentic source, timely and incorrect sequence, and can use conventional encryption and shares a key. So we've actually looked at an algorithm that does this, which is what we kind of did today. Okay. So here's a nice diagram of how it works. Message authentication code, or MAC, is the terminology that we can use for it. So notice we have a message. Guys, any questions over there? So we have the message, that's the plain text message. Remember, we're not trying to achieve confidentiality, so we're basically sending the message as plain text, although we can calculate a MAC on a encrypted thing as well. All right, so we have a MAC algorithm, right? And that gives us the hash, kind of like the one we did today. We can use a key, which we kind of used that today. And so now we have the message and the hash, and that's what we send over the internet to receive on the other end. and then we take the message once again, right? We take that message once again, run it through the same MAC algorithm, and get a key, a hash, and compare it to the hash that we sent, and they should match. And that's basically how we know that it meets integrity. Does that make sense? If we change one bit of it, it's not going to give us the same hash, and therefore somebody changed it in some way. Okay? Yeah, so that's kind of the idea. I like this graph or figure because it kind of encapsulates the definition, a nice definition for hash, secure hash function. So notice it says message or data block M of variable length, and notice it's L bits, much bigger, goes through a hashing function, and it generates a hash value, and notice it says a fixed length. So it's like we have a variable length that's bigger, sequence of bits, and we get a fixed length, smaller hash value. Okay, and you've seen that with OpenSSL because we had MD5, SHA-1, SHA-256, and they got a little bit bigger each one. But this is the block diagram of secure hash function and its definition, basically. Any questions on this idea? That's, if I ask you define a hash algorithm, that's, pretty good definition. The algorithm is different, right, than the goal of it. If I ask you to write the algorithm, you just write the algorithm we wrote this morning, or sorry, earlier today. All right, so a few requirements on hash functions can be applied to a block of data of any size. We saw that. That text message could have been as long as you wanted it, right? All we have to do is take that message, break it into blocks, and do the encryption. But it produces a fixed length output. That was the value that we produced, well, size 8. It's relatively easy to compute for any given X. You saw it was pretty straightforward, just an XOR operation with all the blocks. And yet, it's difficult to go from the hash back to the original message. Okay, so it would be hard. Okay, so that's kind of the idea. There's approaches again to break hashes. Cryptanalytics, logical weaknesses in the algorithm. Or brute force, guessing things, trying everything until you achieve what you want. SHA most widely used hash algorithm. And some of these, as I said, use passwords and so on. Later on, we're going to look at uses of hashes for other applications, like we're going to tie it to malware. So obviously in malware detection, hashes are used. Do you guys know how that works? How does an antivirus use hashing? So if you think about it, right? You have what is a malware? It's code, right? Some program, say Python or an executable. So would you agree that it's a file of bits, right? And it's like a specific arrangement of the bits. So that file, which is a virus, you could use OpenSSL to do what? Hash it. And it's going to give you a hash value. Do you see that? And so if somebody detects that virus in a computer, they know, okay, this file is a virus. So let's create a hash of it. And then now all you need is the hash value. What happens is that becomes part of a database. So when you have something like McAfee or Symantec or whatever it is, that's what they have, a whole list of hashes. And so what they're doing is they're looking at all the files in your file system and hashing them. And then guess what? If they find a file, right, that they hash and produce the hash, and they look in their database and it matches, it's gotta be the virus. You see that? Does that make sense? So that's how antiviruses work. Go ahead.
Can you just put random letters and stuff around it?
That is called a polymorphic virus. That's the solution. So when a virus replicates, you're right? It's a very good observation. When you replicate the virus, what should you do? Put a random letter in it, and boom, hidden. But so would you agree that you're paying McAfee a lot of money maybe for something that's not that great, right? Because yeah, that'll escape the hashing technique. Very good observation. Those are called polymorphic viruses. It's very easy to do. But that being said, if someone is not that clever, there may be a virus. If it's the exact same copy and you've hashed it, you can find it. But yes, very good. Any other questions? All right, so we'll do some of that later in the semester, a lab, and we'll hash some files. Okay, so let's go ahead and keep going. All right, so I think we're ready for so that kind of is integrity also, kind of the last set of slides of that. And now we're moving into the kind of the new topic, which is limitations of symmetric secret key encryption. So that we already know the limitation, right? So the fundamental limitation of symmetric secret key encryption is, how do two parties agree on a key? So we've established already that basically they have to meet out of band, which means they meet at a coffee shop and exchange the key, right? But that doesn't work in today's era of the internet. Like, you don't have time right now to go to your bank and get a password so that you can do banking, and then go to Brightspace and do that, and then Amazon and do that, and then think of all your streaming services and all that stuff, right? So that can't happen like that. So in order for Alice and Bob to communicate securely, they need to agree on a secret key, because we are still going to use symmetric key encryption. We are still using these algorithms. The problem is we need the secret key. So in order to agree on a secret key, they need to be able to communicate securely. So it's a whole chicken and egg problem. What comes first? The agree on the secret or establish the communication, right? So we got to figure out a better way of solving that problem. So this problem is especially common in the digital age. We constantly end up at websites with whom we decide we want to communicate securely, like online stores, but with whom there is not really an option to communicate offline, to agree on some kind of secret key. In fact, it's usually all done automatically, browser to server, right? So we'll do a lab that is going to be client to server, basically, architecture of PKI. So that's next week. So in fact, it's usually all done automatically, browser to server. And for the browser and server, there's not even a concept of offline. So they only exist online. So we need to be able to establish secure communications over an insecure channel. Symmetric secret key encryption can't do this for us, okay? So it can't do this for us. So that brings us then, remember, we were talking about symmetric encryption. That's when we have one key. This takes us now to the new topic for week 4 and the next week's, which is asymmetric encryption, all right? So in asymmetric encryption, also known as public key cryptography, both communicating parties, i.e., both Alice and Bob, have now 2 keys of their own, okay, which are called the public and private key. So another way of putting this is that the way that you're doing symmetric encryption right now, all of you have 1 key for symmetric encryption. But now you will also need to do another type of encryption called asymmetric encryption. And for that type of encryption, you're going to have to create a new pair of keys, which is going to be 2 keys called public and private. And all of you will have a public and a private key of your own. Okay? So that's the trick, the solution to this. So again, so in asymmetric public key cryptography, both communication parties, but Alice and Bob, have 2 keys of their own. So just to be clear, that's going to be 4 keys in total for the communication between Bob and Alice. Each party has their own public key, which they share with the world. So what that means is you'll create your public key. You can have your own website and you just put it there. It's available, free to everyone, for everyone to see, okay? That's the public key. So which they share with the world. And then they also have a for that public key, they have a corresponding private key. And that's, as the name implies, is private, and which should be kept private as a closely guarded secret. So you do not share your private key with anyone, ever. Okay? You'll do some exercises with a partner, and you can send them the public key now, but you should never ever send them the private key. Okay, it's your key. But you generate a public key, and from that public key, you generate the private key. So they are linked mathematically. Okay, and so that's what RSA does. Okay, and that's what we're going to look. So we'll spend quite a bit of time on RSA to understand that algorithm, and you will see it's actually a lot of algebra. So it's not really like it's math, but it's like really nice. It's algebra. Okay, so you'll see it's kind of interesting. All right, yeah. So anyway, so asymmetric is like the framework, and RSA is the algorithm. Okay, remember. So RSA is like the solution that 3 people invented of how to implement this idea of asymmetric encryption. There's another approach, Diffie-Hellman, but RSA is like the the more solid one. Okay. All right. So kind of more information. So asymmetric, or also called public key encryption. The magic of public key in cryptography is that a message encrypted with the public key can only be decrypted with the private key. Okay, that's the corresponding one, right? So you generate a public and a private for each person. So for that public key, the magic of public key cryptography is that a message encrypted with a public key can only be decrypted with the private key. So for instance, let's think about this. Alice will encrypt her message with Bob's public key. Okay? And even though Zelda knows she used Bob's public key, and even though Zelda knows Bob's public key because Bob has it on his website, right? It's available right there. She is unable to decrypt the message. Why? It can only be decrypted with Bob's private key, and Bob keeps that one private, secret. You can see that only Bob, using his secret key, which should say private key there to be more clear, using his private key can decrypt the message, assuming he's kept it secret. Got it? So we'll do several exercises of this. This is really important. We don't actually encrypt the message with RSA in general practice. We only encrypt what? What's the thing that we needed to share securely? The secret key of the block cipher, right? The symmetric, for the symmetric, we still use symmetric encryption, but we needed to share that key. So now this is what we're gonna use to encrypt that key and send it securely. And then once we've shared that key, we can just use AES, basically. So we don't actually, and the reason being is that we will see in one of the labs, RSA can be a bit slower than AES or asymmetric. Another way of putting it is asymmetric can be slower than symmetric. And so if you're downloading a movie, just to give you like an exaggerated example, if you were doing everything with RSA, it might take you 10 minutes. So people may not want to wait 10 minutes. But if you're only decrypting the key with RSA, then it's fast. And then you decrypt the movie with just block ciphers much faster. Got it? So that's the idea. So it's interesting how SSL and such frameworks are a combination of security, but also like practicality, right? It's got to be fast and useful and also secure. So it's almost like you find a nice, perfect balance. Okay, just enough security, but also make it usable. Okay. All right. So I have this pretty sophisticated graphic kind of to illustrate this idea. All right. So, but this kind of captures everything that we're doing, right? So we've got Alice and Bob. So think of Alice and Bob. They generate private and public key. Okay. So here the direction is that we're sending the message to Alice. Now, currently, we are only concerned with which principle of information assurance for this? Confidentiality, very good. We don't want the key to be known, right? So we're protecting the key. So we've got the plain text message. We're going to encrypt it, right? And we need, so Alice is sending the message to Bob. So then Alice will need Bob's public key to encrypt the message. Does Alice have access to Bob's public key? Sure, it's in a website somewhere available. So then Alice takes the plain text, takes Bob's public key, encrypts it, and creates the ciphertext. Now the ciphertext can't be sent over the insecure internet. So you send it, Zelda is snooping, okay? And Zelda, let's think about it. Zelda has the encryption algorithm, sure. Zelda has Bob's public key, but yet she still cannot decrypt the message, all right? Now the ciphertext is received on Bob's computer. Bob uses a decryption algorithm, and Bob will use his own private key to decrypt the message. Only he has the message. Now let's think in reverse. Bob wants to send a message to Alice. How does that work? Mm-hmm. Yep, exactly. So now Bob is going to take the plain text message, is going to use Alice's public key, sends it. Alice is going to decrypt it with her private key. Got it? All right, so now let's think about authentication. So this achieves confidentiality, right? Can you think of a scenario where you would achieve authentication with this same framework? First of all, let's define what authentication means, right? So what does authentication mean? It means that Bob receives something and Bob knows that it came from Alice. That's authentication, and no one else in the world. Only Alice could have sent that. How could you use asymmetric encryption to achieve that? What do you think? Without modifying this. What do you guys think?
Because only the one private key answers the public key.
Yes, that's true. So how would that work? Like run a message that achieves authentication somehow. Think about it a little bit. So it's good to think in terms of Bob and Alice, right? So think Bob wants to send a message. She doesn't care about confidentiality. So you don't have to worry about confidentiality. Just worry about authentication.
So doesn't Bob have to ask Alice for his public key?
The public key is available. He doesn't have to ask. It's in a website. Bob can literally go to alice.com and it's right there.
Bob
Yeah.
encrypted with his private key and it gets decrypted with public key.
Okay, so let's run through that idea, right? Bob takes the plain text and encrypts it with what? His private key. Mm-hmm. Yeah, go ahead.
He decrypted with his public key.
And everybody has access to that key, right?
Yeah.
And only that key would decrypt a message encrypted with that private key, right? That's it. Exactly right. Do you guys get it? No? You don't get it?
A public key to decrypt a private key. Or
A message, right? So a message encrypted, you could encrypt a message with so that there's like a duality, right? So if Bob uses his private key to encrypt a message, right? Sends it to Alice, what can Alice do? She gets that message and she decrypts it she doesn't have Bob's private, but she has the corresponding public. So she decrypts it. Now, everyone in the world can decrypt that message, actually.
but you know that it's from Bob no matter what.
Exactly. So does it achieve confidentiality? No, because all of you would be able to go to bob.com and get his public, so you will know what it says.
But Bob can't get it.
Yes, it's authentication. So only Bob's private could have generated that. You guys see that?
Yeah.
So that's kind of the general idea. To implement it, it's a little bit more involved, and we'll combine hashing with it. So we'll see how that works. But yeah, that's the duality of it. So it's really nice. So nice job. Got it, guys? Any questions on this one? All right, so I think that's the slides, okay? So I'll just kind of, in the last few minutes, motivate the lab for this Thursday, and then we'll wrap it up for today. All right, so let me, yeah, I think that was the last slide. All right, so hopefully that makes sense. So let me